Greetings everyone, and welcome to a video lecture for engineering numerical methods. We are currently covering Chapter 9. Chapter 9 covers numerical integration, and we will talk about several methods, including the trapezoidal method, which we have been introduced to in a previous lecture, Simpson's method and some of its variants. We'll also discuss Gauss quadrature, some of the MATLAB built-ins that are available to help you, and we'll at least touch on the beginning of Chapter 10, which is ordinary differential equations. So, we have already talked a little bit about the trapezoidal method, and this is derived from taking a rectangle and basically a triangle and adding them together in order to fit as closely as possible to the area underneath a curve. We use a linear function for this to approximate the integrand over that interval, and all we need to be able to do is to calculate the value of the function at the 2 points and know what those 2 points are. Graphically, what we're doing is creating this square, that's the FA times B minus A, and we are also getting the triangle, which is where the 1/2 comes from, the B minus A, and the FB minus FA. As we looked at in class, and as we'll look at momentarily when we take a look at the program that performs it, we can improve the accuracy of the trapezoidal method by breaking up the trapezoid into smaller and smaller pieces. This should be a very recognizable kind of thing. It's the same thing we do when we're performing integration in your previous math classes. So as things get infinitesimally smaller, we get more and more accurate. From the standpoint of formalizing this into an equation, we are taking the summation of the previous equation we looked at over n total intervals. If we choose to, we can make these intervals all the same size, or we can have differing sizes of integrals, or of intervals. Usually people will tend to do consistent sizes. It's a little easier to wrap your head around, it's a little easier to program, certainly a little bit easier to look at visually. If we are using a consistent subinterval, we generally designate that with a variable letter h. So we're making h smaller and smaller. We're taking points along the independent axis that are closer and closer to one another. Let's take a look at how this is done with the program. I know we've already done this, but we'll do it again. Example 9-1. So example 9-1 is a very simple program. What it's doing is taking an interval, which can be either programmed as a 0 or a 5, or typed directly into a call to a function, a user function, which we'll take a look at momentarily. You can see that I've been playing with this program a little bit beyond what we've been doing in the book. This is the one that is used for the example problem in the book, the vel equals equation. Go ahead and save and run that. We'll take a look at the results momentarily. This is calling a function called trapezoidal. Trapezoidal is a very, very easy function to understand. It just automates that equation that we looked at a short time ago for performing the trapezoidal method. This is using the composite trapezoidal, so we do have an input value of n for the number of sections that we want to break that trapezoidal integral into. You'll note that the first thing we do is compute the value of h, the subinterval that we're going to be working in. Then we break up our x value so that it's between the two areas in which we want to compute the integral, with a step of h. We perform the function that has been put into us via the call to this user function. We do this over the entire range that we've created, that x range. Then we compute the integral using the composite integral formula that was shown in the notes. I've already run this, and you'll see I've run it for quite a variety of input values. Let's take a look at this again. What I've done is run it between the areas of 40 and 93 for this equation, and I've run it with a number of different breaks or number of intervals along the x-axis, anything from 1 to, let's see, 10 million. And this displays how the accuracy will change. So we've gone from 567.7, running it with just one interval, to 574.15, running it with 10 million intervals. You'll note that once we got up to a certain number of intervals, this didn't really change at all. Our answer remained quite constant. So we're definitely approaching a point of diminishing returns in accuracy as we increase the number of intervals. Now, it's always a good idea to kind of get a feel for what it is we're looking at. So I always recommend trying to plot the thing that we have been solving. Our formula is still in here. This was set up as an anonymous function, so here it is. Let's go ahead and try this. Why don't we say that we'll have an x that is equal to 40 to 93, and we'll plot that x value against the value of the function. So here's what we're looking at. And what we see is from 40 to 93, we have a slight curve to this. Let's throw a grid on there and get sorry. We see that we've got a slight grid. Remember, what we're doing is computing the area underneath this curve. Because this is slightly curved, we're not getting something exact when we try and do that trapezoidal method with just one interval. We are at 567. As we break it up, we see that this is much closer to 574, basically 574.15. So this is not a great example of how we get better accuracy in the trapezoidal method by breaking it up, but it's the one that's in your book. I'll take a brief break now, and then we will continue with the lecture. Greetings everybody. So hopefully you had an opportunity to play around a little bit with example 9-1. If you have not played with the program, please do so. It's kind of interesting to look at. Now that we've finished talking about the composite trapezoidal method, let's move into our next topic, which is Simpson's method, where the trapezoidal method uses a straight line between the two outer points of the interval where we are trying to calculate the numerical integral. Simpson's method uses a quadratic or a cubic approximation. So if you have a complex function, Simpson's method can be significantly more accurate. This was named for Thomas Simpson in the United Kingdom. But it was actually used by Kepler even more than 100 years earlier to Simpson's actually publishing it. So let's take a look at how this is generated. We'll first look at the variant called Simpson's 1/3 method. And this uses a quadratic polynomial. And the quadratic polynomial is generated from the intervals start, finish, and midpoint. So we have first, an x1 at the start, that's a, the start of our interval under question. The point in the middle, which oddly enough is computed just as the average of a and b, and the point at the end, which is b. From those points, we generate a quadratic equation, generally termed p of x. And we need to create that quadratic equation such that p of x sub 1, which remember is the start of our interval, is equal to the value of the function at that starting point. P of x sub 2 is equal to the value of the function at x2. P of x3 is equal to the value of the function at x3. We do that by setting up the following coefficients for our quadratic equation. Alpha being the value of the function at x1, beta being a composite of the values at x2 and x1, and gamma using x3, x2, and x1. You'll notice also that in all of these cases, all of these equations that we're looking at, and also with the numerical differentiation that we looked at in Chapter 8, that interval, the portion of the interval over which we are computing each of these values, is quite key and defines for us a large portion of how accurate our solution will be. Once we have these coefficients, we can therefore say that the integral of the function from our starting point at x1 to our finish point at x3 can be approximated with the following equations. So these are fairly easy in order to generate into a script, which we'll do momentarily. Graphically then, what we're saying is, if we have some function f of x, that's the black curve here, we're going to create a nice quadratic, that's the blue curve, using these 3 points. It's important to note that if we do this for any given interval from a to b, that we are creating this with the point at the beginning of the interval, the point in the center of the interval, and the point at the end. So we have 3 points for any given interval, but we are really breaking this interval up into 2 pieces. The first one, which is defined by the h number running from x sub 1 to x sub 2. The second one from x sub 2 to x sub 3. So the 1/3 Simpson's method has even numbers of intervals and an odd number of points to define it. We can do this as a composite type of method as well, just as we did a composite trapezoidal method. And again, we could, in theory, do this with a uniform value of h, or with varying intervals of h. For this 1/3 method, then, the number of subintervals must be even. So just like if we're looking at the picture, we have an even number of intervals for the 1/3, odd number of points. When we break it up into lots of intervals, we need to have an even number of subintervals.
The next method we're going to discuss is Simpson's 3/8 method, whereas Simpson's 1/3 used a quadratic formula to approximate the function. Simpson's 3/8 uses a cubic polynomial. So the representation, p of x, is shown in this formula, where x sub 1 is the beginning of the interval, a, and x sub 4 is the end of the interval, b. X sub 2 and x sub 3 then are used to divide the interval into 3 equal sections. So we have similar end conditions, or similar conditions for the formula that we had in Simpson's 1/3, and a similar formula for the actual value of the integral. Here's what graphically the Simpson's 3/8 method looks like. This is a little bit different than the Simpson's 1/3. What I really want to point out to you is, whereas the Simpson's 1/3 required an odd number of points, so there were 3 points, Simpson's 3/8 requires an even number of points at x sub 1, x sub 2, x sub 3, and x sub 4. Also to contrast, whereas Simpson's 1/3 method broke the interval into even portions, Simpson's 3/8 breaks the interval into odd portions. I've implemented this into a couple of programs. First, an example program that runs through the Simpson's 3/8 and again contrasts it with the trapezoidal method, and an example function that implements it. I'll throw these up on the screen shortly, so please do try them. What they look like when you run them is this. So we've got definitely a function that is a cubic polynomial. We're calculating the area under it. If we compare the efficacy of the Simpson's 3/8 method with the trapezoidal, we can see that Simpson's 3/8 gives us a value of 18.64625. The trapezoidal with one interval is significantly different at 13.2. Again, if we go with a composite trapezoidal with 10,000 intervals, we can match the accuracy of the single calculation in the Simpson's 3/8 method. Okay, so now we've covered Simpson's 3/8 method. It's worth mentioning that Simpson's 3/8 method can also be calculated as a composite. Note that if we're using the 3/8 method, the number of subintervals that we are using for this must be divisible by 3. So as an example, if we used n greater than or equal to 6, the Simpson's 3/8 method would devolve down to the shown equation. You can see this graphically in the picture below. Now something completely different. So for the trapezoidal method and for the Simpson's method, what we're doing is doing numerical integration by using a formula to approximate the points. Gauss quadrature is quite a bit different. This was created by Carl Friedrich Gauss, who lived between 1777 and 1855. And the way that Gauss quadrature works is to solve at specific points known as Gauss points. These are not equally spaced. They don't include the endpoints of the interval in question, and they're selected specifically to minimize the error in calculating the integral. So the general form is written down here. You'll note that it makes use of coefficients, C sub I. C sub I, these coefficients are known as weights, and they are used within the interval AB to correctly generate the integral. From a graphical standpoint, if we take a look at this, you can see that in this case we're doing an integral of the function y is equal to x squared, basic quadratic. If we are solving it between the intervals of -1 and 1, we would normally try and get the entire area just under the curve. Gauss quadrature uses those two special points, the coefficients or weights, you can see them noted here, and calculates in effect a rectangular area which is equal to the area underneath the base function. So this is quite a bit different than trapezoidal or Simpson's. The general form, if we do have that domain from -1 to 1, is shown in the first equation on this page. It's just the sum of I equals 1 to n of a certain number of points, the weights, at x sub I, the Gauss points. So if n is equal to 2, we end up with the second equation on this page, just 2 components. Then we take a look at specific cases where the general form is exact. If, for instance, the function of f of x is equal to 1, we can say that the integral from -1 to 1 of 1 dx is equal to 2. If that's the case, and we substitute f of x is equal to 1 into this equation, we can say that 2 is equal to the two weights added together, c1 plus c2. Second case, if we were to say that f of x is equal to x, we can see that the same equation would become c1 times x1 plus c2 times x2 must be equal to 0. Third case, f of x is equal to x squared. We would find that 2/3 is equal to c1 x1 squared plus c2 x2 squared, and case 4 similarly. Now, normally if we're trying to do the Gauss quadrature method, we may require that x1 and x2 be symmetric about the value of x is equal to 0. So I would say that x1 is equal to negative of x2. If that's the case, then we force our weights c1 and c2 to be equal to each other. If we use the previous equations, that gives us the following values, that c1 and c2 must be equal to 1, and that our Gauss points are equal to -1 over the square root of 3, or 1 over the square root of 3. So this then gives us an expression for the integral. Now, that particular derivation is only valid for the values from -1 to 1. If we want to use Gauss quadrature to some generalized domain of A and B, we perform a transform. It's accomplished with the following method. and gives us the equation at the bottom of the page. So it's reasonably straightforward. Now, we've covered a few different methods, so it's time to talk about what MATLAB gives us as built-ins for numerical integration. The first thing we get is the quad function. The quad function allows us to integrate some nonlinear function, and it actually uses a modified form of Simpson's method, modified in that it makes for greater numerical stability. There's also a quad L function. This uses the Lobato method, which we're not studying exactly, but again, it's a modification of the things that we've been looking at. Finally, MATLAB does implement a very basic trapezoidal method. It's using data vectors. Recall that when we're doing numerical integration, we're generally working with points. And that ends what we're talking about for Chapter 9. Next lecture, which I will be in town for, is moving into Chapter 10. We'll also cover Chapter 11. So just to give you a brief feel, we're starting to look at ordinary differential equations, specifically initial value problems. The ordinary differential equation is an equality that involves a function of one independent variable and the derivatives of that independent variable. Equations of this form are very common in engineering problems, particularly for those that use time as one of the variables. So we will be seeing that in the next lecture. In the meantime, guys, thanks for paying attention. Please do, again, take the opportunity to go through and type out these programs, type them in, try them, mess around with them a little bit so that you can gain that experience, and I will look forward to seeing you at the next class.